So I'd encourage you to be there for that. We may have base, I'm still negotiating. But anyway, should be a fun talk. We say a couple words about the homework for next time. Well, this week. You all probably seen something like this when you when you're out right over talking on matrix or whatever. You might ask yourself what the determinant is. What you have is you have all matrices in this form of cosine theta, sine theta, minus sine theta, cosine theta, where theta is an R. Show this is a subgroup of all 2x2 invertible matrices. And of course, this is under multiplication. Show that the operation given by M operating on B is MB is an action of G on R squared. I'm going to define what an action is actually today. And explain geometrically how this action works. It actually does something that's quantifiable to these vectors in two space. Number two, these are there's a couple of like really nice little results in this homework that are important. If you have a homomorphism of groups from G to H, and X is an element of G, show that if the order of X is some number N, and X to the K is 1, then N actually must divide K. And 3 is a related problem. If the order of X is N, then the order of phi of X divides N. Number 3, the homework, second week homework actually might help you. Number 3, consider the subgroup of the symmetric group on 9 letters generated by these permutations 1, 7, 3, 5, 2, 6. And why is this? Find the order of the subgroup generated by X and Y, and it's probably a familiar group. See if you can tell me what it is. Number 4 has 4 parts. The last 2 are extra credit optional. By the way, when you do those problems, good for you. I applaud that, but I'm going to be even more tough on the details on the G problems. Define the collection or define this set. Well, G's a group. We define ought G to be the set of all automorphisms from G to G. Notice one of these automorphisms is the identity automorphism. Show that these automorphisms actually themselves form a group. Suppose we define phi sub G from G to G by phi G of X is GXG inverse. Show that that is an automorphism. And then we've got these 2 other ones. The correspondence G goes to phi of G as a homomorphism from G to odd G. What is its kernel? These terms will come up this week. Consider the collection of all phi G and G and G. Well, all phi G for G and G. We call this collection INNG for the inner automorphisms of G. Show that this is a subgroup of the automorphism group. And is it normal? We'll discover what that means pretty soon. And finally, let G be a group and X, Y, and G of orders M and N respectively. So I've had actually a lot of questions independently about this. This is where we're going to get to the bottom of. What happens if you take an element of order 2 and multiply by an element of order 2? Well, unfortunately, in general, you can get any dang thing in the universe, right? But if X and Y commute, so if X times Y is Y times X, then the order of the product must divide the least common multiple of the orders of the elements. So show that. And in part B, show that if XY equals YX and also the subgroup generated by X intersect the subgroup generated by Y is only the identity, then the order of XY is exactly equal to the least common. Okay, so should be some fun problems for you. Any questions? Okay, so the last thing that we were talking about was this thing that I mentioned called the subgroup criteria, which I will read for you here. Let G be and H non-empty subset of G. Then H G is a subgroup if and only if for all X, Y, and H, X, Y, and H. This is really kind of groovy in the following sense. Sometimes you want to know if a substructure of G is actually a group. Is it a subgroup? How can you tell? You got a one-line thing. If you can show that for any pair of elements, X and Y and H, that X, Y inverse is an H, it's automatically a subgroup, right? So why does this work? Yes.
What's the less than equal to sign?
So that's a good question. You're familiar with the subset sign?
Yep.
Group theorists sometimes use this for subgroup, so I do that notation. So it's like subset, but often they use the standard less than or equal for subgroup, and I'm attempting to conform to that. But I might use either notation, but I'll make it clear when it's a subgroup. Okay, so let's look at it, shall we? Proof. If H inside of G is a subgroup, and X and Y, then Y inverse is in A, and so is X, Y. So that direction is not too bad, because if H is a subgroup in the first place, and you have two elements in H, then because it's a subgroup, it has to contain Y inverse, and because it's closed, it has to contain X times Y. Is everybody okay with that? Mm-hmm. The interesting part is this is all you need to get that it's a subgroup. So here is, this is the sexy part. This is actually important. H is not empty. So there exists X and A. I agree with that. Now, note, and I say this for dramatic purposes, X and X are in H, right? See, that's a little redundant, isn't it? But I do it for dramatic purposes because what is my condition? If I had any two elements of H, didn't say they were different, then this has to be an H.
What is that? The empty set sign?
Yes.
Oh,
H is not empty, and that's the assumption we had on the set here. Sure. Okay, so now we know that there we go. E is in H, right? I agree with you. So that's one of the things we need. What else? Yes.
How do we know that the inverse exists in H and it's not just like in G? Like, how do we know? Like, we know X is in H, but how do we know?
Oh, I didn't say that the X inverse was in H. Well, our criterion is this: if you have two elements in H, X and Y, then X times Y inverse has to be in H, right? And so in this case, my two elements are X and X, so X inverse. So this forces the identity. So here's my step one. I know that the identity is in the subgroup or in the set. Yes.
Oh, yeah.
Okay. Now. So now not only do we have X's in H, we've got the identity as well. Therefore, this is such cheap. E times X inverse. So now we've got that, right? So we're kind of building back. I know that H has the identity. I know that if any element is in H, then its inverse is in H. What else do I have to do? Well, now, suppose X and Y are in H. We know Y inverse is an A. Because we built that. So X, Y inverse is an A. And so is X, Y inverse, inverse. Which is X, Y. So by building back, I've done this. Let's collect what I've done. Direct again. This is H. What do we know about H? It's closed under the operation. Contains the identity. It contains inverses. What's the one thing that I left out? Associativity. Why do I not need to say anything about that role? Because G itself, the operation is associative, so it's certainly associative in the smaller bit, right? Everybody agree with it? And so there's the subgroup criterion right there. If it's a non-empty set and you can verify for every pair of elements X and Y, XY inverse is still an H, then you're good to go. Okay. Any questions on that?
Where are those 3 dots?
What 3 dots? These?
Yeah.
That means they're important. Yeah, those 3 dots. Okay, other questions? Let me give some subgroup examples, if you will. We looked at some last time. We looked at subgroups of C6 and S3. The rationals numbers under addition is
I'm a little bit confused about that step. Why does having the identity at H, having X and H mean that the identity times the inverse is in H?
that's the property that we assumed. We assume that if you have any pair of elements, Bill and Fred, and Bill times Fred inverse has to be. All right. So my 2 elements here are the identity X. So the
Oh,
identity.
so identity X and okay, right, that makes sense.
Other questions? For example, the real numbers under addition, all kinds of subgroups. The rational numbers, the integers, 0, right? These are all subgroups. Here's kind of an explicit. I like this. I'm gonna look at D6 here. Remember, we've got a rotation and flip, right? I'm going to use this labeling to describe D6 as a subgroup of S6, symmetric group on 6 elements. Let me point out that whenever you rearrange this puzzle piece and put it back in some order, what have you done? You permuted those corners. Everybody agree with that? And you don't put this back and it becomes a pentagon, right? That permutation of the corners has to be 1-to-1 and onto. 6 corners, whatever, you're going to still get 6 corners. Right? Can somebody describe what the rotation looks like in S6? Let's say I rotate that 60 degrees clockwise. If I go 60 degrees clockwise, where does 1 go? 2 goes to, which probably is why I labeled it the way I did it. Right? Oh, audience participation. Yes, you're going to be flipping around the x-axis and the y-axis.
One.
Okay, flip it around the y-axis. When I flip this about the y-axis, can you describe what happens to the corners now? Where does 1 go?
Oh, 1. 1 stays the same.
1 stays the same, and so does 4, I guess, right? How about 2? Where does it go? And 6 goes? And it also swaps out 3 and 5, right? You can check. You do this twice, you get the identity, and if you rotate, that's the center, right? Now, here is a bit of magic. What happens when we have S or S? Let's write this out, shall we? 2, 6, 5, 3, 1, 2, 3, 4, 5, 6. And then 2, 6, 3, 5. When doing these computations, you can start anywhere. Well, I'm gonna start with 6 for reasons which might become clear. What happens? Where does 6 go? It goes to 2, to 3, to 5, and it's done. Do I agree with that? Where does 5 go? Ultimately ends up at 4. How about 4? No, 4 goes 5 back to 3. Where does 3 go? 2. Good. And how about 2? 1. And 1 better go to 6. Better check it, but it does. Right? What is this? 6, 5, 4, 3, 2, 1. That's spinning this counterclockwise. So notice, without even thinking about it geometrically, we've thought of D6 and 12 rearrangements of this as a subgroup of S6. And the computation it just worked out for us very nicely. By the way, somebody remind me, how many elements does S6 have?
12.
No, S6. Yeah, it's got 7, it's got 6 factorial, and this has only got 12, so this is a little tiny small subgroup of S6. And in fact, if Cassie had chosen to spin it around the x-axis, the S would have been 3. If you might try to do it this way, you'll get the same result. You'll have a different S, but it will still satisfy this relation. There are actually many copies of this group since inside S6. A lot of.
To flip around the x-axis,
What's that?
can you only flip around the x-axis and it's?
Well, the way I've drawn it, right, because that's right, you can get away with doing this because it's in, because it was a pentagon, it wouldn't match up. I flipped it, right? Okay, other questions? Okay. I'm going to introduce you to this concept now. We're going to do more extensive work with this because this concept that I'm going to introduce now is basically the reason for, well, one could argue this reason for talking about groups in the first place. Groups act on other sets. They can permute things, just like this group here in inside of S6, the subgroup acts on that hexagon subgroup by turning it into space, and you're looking at symmetries and so on. This is why things like this are important in things like chemistry and physics, because you study symmetries and so forth. So this concept is called a group action. And like I said, we're going to do it more extensively later, but for right now, I'm just going to kind of tell you, yes. Let's suppose A is a set, we'll say not an entity. A group. A group action of G on A is a function G cross A in that A. So in other words, I can combine an element of the set, whatever it is, with an element of the group, and it barfs out another element of the set. Well, I'll write this as G dot A. This is G acting on A. It's sort of like a function. And this actually has some properties. Number one, I want this actually to be nice and following sense. I want G1 acting on G2 acting on A. So let's think about what's going on here. G2 acts on A, and this gives you a new element of A. And then this acts on that new element of A. How do I want this to act? This should be the same thing as G1, G2, which is an element G acting on A. And 2, E acting on A is A. And I should fix it all this for all G1, G2, G, A and A. This one is for all A and A. So you want the identities to basically leave everything in the set alone. And you want it to behave in an associative fashion. Here's some examples of actions. You can act on itself. Just the ordinary group multiplication. All right. And actually, this seems really silly, right? It's like I'm making up something just so I can ask you some stupid definition on the test, right? But a group acting on itself, as I said, actually is an incredibly useful tool for being able to do a lot of our theorems. Notice this action behaves both of these because this works because the multiplication in the group is associative, and this works because the identity times anything in the group is itself. I'll give you another way you can act on itself. And there are many. This is an important one. So I'm gonna do that this way. I'll prove to you that the second one is an action. I write them separately like that just to emphasize that these two are from the group and they're acting on this element of the group. If you look at G1 acting on G2 acting on X, let's see what this is. This is G1 acting on. Okay, my rule here is this is G2 X G anyway. Everybody agree with that? And this is a new element of the group. Now G1 acts on this junk by conjugation. Everybody okay with that? Yes.
So inside the parentheses there, you're just doing ordinary for multiplication, or what is?
That's right. The circle means conjugate and just,
And so then that part.
this means ordinary.
Okay.
So this is G1, G2, X, G2 inverse, G1 inverse. You might tell me how to rewrite this last blob here? The two inverses? Yes.
G1, G2, all in.
Perfect. Agreed? And this is G1, G2. Acting on X. Right, because blob X, blob conjugate. Or blob inverse, I should say. Okay. And the identity. See what happens. You have E operating X. This is E X E inverse, which is X. So there you go. So this conjugation is group action. Okay, any questions?
How do we get from the last one, how do we get?
Here to here, because the rule is, what is the rule? The way G acts on X is it goes next to X with its inverse in the rear view. And that's exactly what we have here. G1, G2 with its inverse in the rear view.
Okay, thank you.
Okay, here's the group is all rotations on the cube, and your action is act, right? There's an action, right? Here I'm composing some things. This is a group acts on this, the group of all possible rotations of the cube under composition that acts on that Rubik's cube while commuting. And that's how you can use group theory, for example, to figure out how to solve the thing. Okay, group actions are, I'm going to give you one last example, and I'm going to show you the details. I gave you two examples of group acting on itself, and here's one that's more exotic. You can see why I'm not going to go click the details of this. Notice that, for example, theta is 0, this is the identity matrix. Right? Agreed? This and how does G act on R2? Well, and D when R2. So how do I let an element of this group act on a vector in R2? The action is I just multiply it like I was in 3110. I just take whatever matrix that is, the cosines, theta, and all that business, and I multiply it by this vector. What does that do? It spits out a new vector in R2, right? Check that this is a group action. So this is an example of something that actually acts geometrically, actually, on the plane. Okay, any questions? Okay, so here's a collection of important groups. Definition, and these are defined via activity basis. When stuff in G group Oh, actually, I won't, I'm gonna make this clear here. Actually, in this case, if this definition, I want A to be a non-empty set, and I want it to be a subset of G. Number one, this is called the centralizer of A and G. This is the set of G and G such that G and G inverse. I did get away. Actually, it doesn't really matter, but I'm gonna stick to my definition. And that should be for all A and A. Centralizer. A. Notice that this is called the centralizer. This means basically it's everything in G that commutes with everything in A. But because notice if you multiply on the left by G, this is AG equals GA. Right, and so this is basically everything in G that commutes with everything in A. This is called the centralizer of G and A. Along these lines, see, let's see G. Is center G. Number three. So I'm gonna leave that. The normalizer of A is the set of G and G such that G G inverse of AG equals A. Now, I know you're dying to ask it. What do I mean by this, right? Because A is a set, right? I know what I mean by this because this is an element. This is G inverse times A times G. But what do I mean by conjugating a set? Well, this is just, this is itself a set. This is a set of everything on this point. Right, so I think the notation is suggestive. A is a set of things, maybe A1, A2, all the way up to A10. This is a set of everything in the form G inverse A1G, G inverse A2G, so you just go to the top set at the same place. This is called normalizer of A and G. And actually, I say it's immediate. I think I'm gonna prove this. Center. Yeah, it's still working.
That's still part of the definition, or?
No, not really. This is a statement of fact here. And I'm gonna show it. Notice the center of G. What is this? this is the stuff that commutes with everything in G. Is it empty? Can it be empty? What has to be in the, what's always in this? The identity. So this is, notice, by the way, the identity element is in every one of these things, right? So these are all non-empty. It's pretty easy to see because notice this equation here is the same thing as writing so really, this is a special case of this. So the center of G is the centralizer in G of what? So I claim that this thing is exactly this thing for a good choice of A. What choice of A could I make for this that makes it equal to this? That is correct. The centralizer in G of G is everything that in G that commutes with everything in G, right? Which is exactly what this is. Contains at least that. The fact that this is contained, that the centralizer in G is contained in the normalizer in G is fairly straightforward because if you're in the centralizer, then this always holds. Therefore, this set has to be exactly equal to this set, right? Well, why are they subgroups? Pick one. Pick centralizer in G or normalizer. I'll prove either one of them is a subgroup. I'll let you do the other one. How many vote for a centralizer? How about normalizer? I think the normalizer edged it out. Normalize, you want to see me prove that because that's you're dealing with sets there. That's a little bit maybe hard to wrap your head around. Probably a good choice. I just want to show off my fancy new subgroup criteria. That's what I'm all about. So let me point out first, the normalizer in G is not, the normalizer in G of A is not empty because it contains what? For sure, the normalizer, what's elements in there? Yeah. Great. So let's let okay, good. This means I agree. That's what it means for X and Y to be normal. These sets are the same. Yes.
Is there, I know you're saying it's the sort of like, you should take what was the elements that can you, but couldn't you write X?
Not the normalizer.
X anchors? Okay.
Yeah, the normalizer is something different. So for example,
So is there like a left normalizer and a right normalizer?
no. So if you look at X inverse AX, this is the set of Everybody agree with me? So, let me make, an observation here. Yep. Says have to be the same. Anybody tell me why? Sort of, right? So, very this, the, well, so such that, right? And not only that, everybody is covered. So, right, so AY is equal to YB. That is to say, for all A and A, there exists B and A such that, AY equals Y. And every YB is covered as well. So these two sets, everything in AY, everything in AY has to be in YB. I'm so fine. Agree? Because an arbitrary AY is on YB over here. Symmetrically, basically it's by Bersley's process. So, if Y is in the normalizer of G of A, then YA equals to AY. Using the same argument, we also have A is equal to Y. Replacing Y with Y inverse, I can use the same argument. So this is kind of an important thing we've got here. If Y inverse AY is equal to A, it's Y is normalized, then it works in the other direction. Right, just sets contain each other. But okay, so far. So here's the final step. To show this is a group, consider X, Y inverse A, X, Y inverse, inverse. This is equal to X, Y inverse A, Y inverse inverse. Okay. What is this? Well, this is A because Y is the normalized. So this is X A inverse. Right? But this is also A because because that's what we proved here, you can lead with an X or a Y. So our conclusion therefore is when I conjugated A by X, Y inverse, I still got A. So X, Y inverse, A, X, Y inverse, inverse. Oh. My fault. I conjugated in the opposite order that I did here. I should have. It actually won't make a difference, but I'll go with that defect. Well, that's my mistake. So I meant to start off. But it'll be the same computation. This is Y X inverse A X Y inverse. And this thing is A because X is in the normalizer. So this is Y A Y inverse. And this is without any substitution. This is more explicitly what we show here. This is equal to A, what we show here. So X, Y inverse to the normalizer. So, so, I'll leave it as an exercise to prove that the centralizer and the center are both subgroups, but actually that's easy. That one's the hardest, is the normalizer. Any questions on that? Okay. That's there here. There. 7. Let G act on the set S. The following are subgroups of G. First one, G sub S. What is G sub S? It's the set of everything in G. It leaves S alone. It's very important in many branches of mathematics to understand sometimes when things act trivially or leave things alone. This is called the stabilizer of S. And I think the notation is suggested in the sense that it sort of stabilizes S in the sense of not moving it. 2, K, which is the set of G and G, such that this is just the stuff that leaves S alone. Now we'll look at the stuff that leaves everything alone. This is called kernel count. So GS is just the stuff that leaves the particular fixed element S alone. And the kernel of the action is all the elements G and G that leave everything. By the way, somebody named something that's always in K. The identity is always in K. Next time we'll go through, maybe quick proof that. See if you can prove that before next time. I hope you all have a good weekend. Don't forget, I've got to be out of the office. I hope to be back at 4:11, but I'll be back no later than that. I've got to speak in front of any questions? All right, y'all have a good one, and we will see you on Monday.